Okay, so we're going to work through exercise 9b of the Pearson Applied 1 textbook, which is about velocity time graphs. Okay, so a velocity time graph, in mechanics we use v to represent velocity, which is usually measured in meters per second, and t represents time, which is measured in seconds. Obviously that's all SI units, which is what we use most commonly. So first example, if we have this velocity time graph here, where it's always at zero. Obviously, if the velocity is always zero, it's a stationary object. In any case, it's not moving at all. Next possibility, if we have a straight horizontal line, then the velocity isn't changing, but it isn't zero either, so it's moving with constant velocity. And the third option, if we have a diagonal straight line, obviously in this case the velocity is increasing at a constant rate, it's a straight line, so therefore we have constant acceleration. So in velocity time graphs, the gradient represents the acceleration of the object. The other important thing to remember from GCSE is that the area underneath the graph represents the total displacement. Okay, if we look at this example here, the diagram below shows a velocity time graph for the motion of a cyclist moving on a straight road for 12 seconds. For the first 8 seconds, she's moving with constant speed of 6 meters per second. Then she decelerates at a constant rate, stopping after a further 4 seconds. So first of all, we need to draw a diagram, which is up here. We need to find the distance travelled, which is the area underneath the graph. Obviously, it's the area of a trapezium, so a plus b over 2 times by h, where a is 8, b is 12, and h is 6. So if we sub those values in and solve it, we get the area under the graph to be 60, so she travelled 60 meters. And then for part B, the rate of deceleration of the cyclist, in case we're finding the gradient of the line, so change in y is -6, change in x is 4, so the gradient of the line is -1.5. Now, we've got to be careful about the wording here. It's asking for the rate of deceleration, so we don't need it to be negative, because we've already covered that by saying it's a deceleration. So the deceleration is 1.5 meters per second squared. Okay, another example. Particle moves along a straight line. It accelerates uniformly from rest to a speed of 8 meters per second in t seconds. The particle then travels at a constant speed for 5 t seconds, and then decelerates to rest uniformly over the next 40 seconds. So we need to sketch a velocity time graph, and then given that it travels 600 meters, find the value of t. So first of all, sketch the velocity time graph. So it starts from rest, accelerates to 8 meters per second in t seconds. Then for the next 5 t seconds, it's traveling at constant speed. And then it decelerates over the next 40 seconds back down to rest. Okay, so there's our velocity time graph. We need to find the value of t now, given that the total distance travelled is 600 meters. So the area under the graph is going to be 600 meters, and we can also work that out in terms of t. So we get 600 equals 5t plus 6t plus 40 over 2 times by 8. And then obviously we can simplify that down and solve it to get t equals 10 seconds. Okay, and now have a go at exercise 9b, please.